Good morning. In some region, maybe it's afternoon or evening. This is Jun Wang Tang. I'm a professor of materials chemistry and engineering in the Department of Chemical Engineering at the University of College London in the UK. Today, I would like to share research results achieved in my group on regional design of photocatalysis for methane transformation to high-value chemicals. In my group, we focus on two technologies. You can see maybe the irradiation technology. One is photocatalysis, and there is a microcatalysis to activate small molecules. The first molecules we're interested in is water, so we tend to convert water to hydrogen gas. And the second is a very stable inorganic molecule, which is carbon dioxide. So we convert this into alcohol and other chemicals. A third one is to activate this very, very stable inorganic molecules, nitrogen, to convert this one to ammonia. And last one, we are interested to activate the small organic molecules, methane, to high-value chemicals. In parallel, in my group, we have two technology. I think that's quite special. One is a time result absorption spectrum, which allow us to observe charge dynamics. And the other is intensity modulated photocurrent and photovoltage spectroscopy. We use this one to work out the charge kinetics. So today, my talk will focus on this one to activate molecules of methane. I don't need to talk too much about importance of methane conversion. I think most of you already know that one. I just want to add two key points. One is I recently found the reserve of the methane, including methane S, is much more than the sum of all the fossil fuels, coal, oil, and gas, which means methane can be abundant feedstock for chemical synthesis. And the other point is every year, substantial methane is wasted. The reason wasted, discuss later, if we can convert a methane to such as even to methanol, you see the market value increased by a factor of 4. So that's very useful. Okay, the reason why we waste so much methane is because methane is so stable. If you count the methane, that requires substantial energy input. So we have to develop a technology to convert the methane with either no CO2 emission or less CO2 emission. So energy must be, I think, from a renewable energy source. Okay, so currently there are 3 routes to convert the methane to methanol by a partial oxidation. One is industrial process, which is 2 process, methane to syngas and syngas to methanol at high temperature and high pressure. And the second route is direct route, so we use either oxygen gas or peroxide or NO2 to activate the methane to methanol. And third route is a cycle. So I'll not talk about this one. It's already used. We know the drawback of this one is a high temperature, high pressure, energy cost too high. I will review the progress of this last 2 routes. Now, route 3, the recent paper published in Science, you can see this very clever design also use copper on the zeolite. So copper first oxide to copper 2+ by oxygen gas, and then copper 2+ will oxide methane to methanol, and then regenerate copper 2+ by water. However, the conversion is quite moderate, and with time, activity decrease, and that's because this regeneration is not 100% efficient. The other 2 recent reports talk about use as an alloy catalyst or as a rhodium on zeolite to convert methane to methanol. Again, need this peroxide or CO as an initiate. And selectivity to methanol, this report is roughly about 45%, and the other one is a little bit higher, is 75%. However, again, the conversion rate of both processes is very moderate, less than 0.1%. So if you summarize the results achieved so far, again, we still need high pressure or high temperature, so energy intensive process. the conversion is a bit low conversion rates, and selectivity also is not very satisfactory. If we can increase that to over 80% better, or 90% maybe much better. And the other safety issue, because high pressure or high temperature also causes a safety issue. And last one is the cost of catalyst. Most cases, the majority report the results still use a noble metal catalyst. Now, further, if we analyze this process, partial oxidation meeting is an exothermal reaction. That means the reaction prefer to operate at a low temperature, as low as possible. So room temperature is the best condition. If we can find the process operate at room temperature, we can save energy, and the process will be safer. Further, if we can increase the conversion from this low conversion rate to high, and with a very good selectivity, plus using a low-cost catalyst, that would be a perfect process. Now, we try to work on that way. So we use a photocatalysis that can operate at room temperature. We prepare different photocatalysts, metal oxide modified TL2. You can see got a population of the different TL2 photocatalysts. Here, just to first analyze the structure of a TL2, which more or less you see the 20-30 nanometer. And on top, we have metal oxide, but the particle size is too small to be seen. So you can see, if you zoom that one, we can see some spots, and that is, I think here is an oxide on TL2, and as a single N, maybe a few N's together as N cluster. Anyway, it's a very small cluster of oxide. And you can see the chemical valence is N3 plus, and we use this metal oxide modified TL2 as a photocatalyst to convert the methane. You can see if we use TL2 itself as a photocatalyst, we can convert methane with about 10% efficiency. When we modify this TL2 by different as a noble metal or other metal oxide, it seems activity decreased. Only when we use N to modify TL2, it gets enhanced activity to 15%. We did some control experiments to prove the necessary condition. When we did this, and the dark condition, very low conversion, nothing. And when we replace TL2 by silicon oxide, again, activity very small. When we remove methane in the feedstock, there are no activity at all. That's true because there's no feedstock. Only when we add lighter TL2 as a photocatalyst modified oxide, we can see very good conversion, and product is methanol and ethanol. Let's further see the selectivity. TL2 can convert methane, but you can see the major product, this one as CO2. Now, when we move to the noble metal, very high selectivity, 100%, but to CO2. Only when we use oxide modified TL2, the major product is methanol, and the second is ethanol, trace amount of CO2. If you work this one, you can see the selectivity to methanol is 92%, and that's 5% overall, 97% alcohol. And then next, we optimize the amount of oxide. We found that 0.33 weight percentage is the best for conversion and simulating for selectivity. Okay, the other reactant we used is peroxide. So we try to optimize the amount of peroxide. When we didn't add peroxide, no activity. When we add a small, is 1% of peroxide, we see very good conversion. And when we further increase to 10%, 11%, we get very good conversion and selectivity to methanol. When we further increase to nearly ratio peroxide to methane 1:1, we see the major products oxygen gas. That's because decomposition of peroxide. And then product of CO2 very close to the amount of methanol, so which is clear to us over oxidation. That's not a good condition. So the best condition here is roughly a 10% of peroxide. So overall, we can get 15% of conversion for methane, and selectivity to alcohol is 97% with 3% of CO2 only. Further, we confirm this process by isotopic measurements. So when we change carbon 12 to carbon 13, major products methanol, see the mass shifted by 1 as proof our product is from methane. And photocatalysis is quite stable, so we run for 3 cycles, almost same conversion and selectivity to methanol. And I see the stability of a catalyst. After reaction, we met the states of N by PS more or less the same as a fresh sample. So that proves photocatalysis itself chemically also very stable. Now I can summarize. On per mole of N, that is an active set for methane conversion, get 18 mole of methanol, and that's much better, I think, than the previous report, as a 3 mole per mole of gold palladium or 4 mole per mole of rhodium catalyst. And further, we see that is our light source, and that is our TiO2 absorption. So only a small portion of the light source get a very good activity. If we can further increase that absorption, and you may see activity better. Next, let's see the chemical state of N. We proved previously is N3 plus. Now, further, when we did this X-ray absorption, near-edge absorption spectrum, we can see our material is black one, overlap with this one, and hydroxide and FeOH. So very likely the active species is one of this. And further, we did some fitting of an ES, and the major component here is FeOH. And then if you look at this fitting results, see Fe oxygen band very close to the Fe oxide, but second shell Fe oxygen Fe, this seems the band much larger than normal FeO Fe in the oxide, and the coordinate number is quite small. So if in the oxide, and that would be 6, now here 3, and that's consistent with our observation by the high TM, because highly dispersed cluster or atomic level of N surface. Next, and the function of N surface. So if we observe the luminescence TiO2 show very strong emission, on add N oxide on TiO2, its emission dramatically reduced. Seems charge transfer between these two species. We did in situ XPS. Before lateral addition, we observe N3 on the surface. When we shine light on the sample, see all the peak shift to the small binding energy. That means N is partially reduced. So clearly proof that's charge transfer from TiO2 to N oxide, and that's electron transfer is a partially reduced N. And further, we test the reduction potential of our catalyst. So on FTO glass, we can see peroxide can be reduced when we add TiO2 catalyst on that one. Reduction process faster. And when we use our N TiO2 as a cathode, and the peroxide can be reduced fastest. So that proves the function of N on the surface. Now further, we use our intense modular photocurrent and photovoltaic spectrum to observe the charge transfer. We call the charge kinetics. Because I don't have time to talk too much about it, but it looks at the results here very interesting. On pure TiO2, the charge recombination constant is very large. When we add N on top, this is reduced by a factor of 6. So charge recombination is dramatically reduced. Now charge utilization efficiency is much better. So here nearly 100%. That means once you get charge separated, and N oxide can use that charge very efficiently. So we put all information together, and that means after lateral addition, we get the electron and hole in our TiO2, and electron transfer from TiO2 to N oxide, as we see reduced N oxide. And this one can substantially facilitate the peroxide reduction that's observed in electrochemistry. And then we can produce peroxide, OH radical. And hole can oxidize methane to get CH3 radical, so these two radicals come together to get methanol. And that's current our understanding. The results look good, but it's not very satisfactory because we still have to use peroxide. Now we variously with a flow system. So that's our gas in, and that's our catalyst bed, and that's our gas source, and the gas flow here through our catalyst bed and comes out. But using the flow system, and that's our the real design, we can use oxygen gas to replace peroxide to convert to methane. We prepare different catalysts. I don't have to talk all. I'll just give you a few examples. So we put either platinum or copper on surface TiO2. We see on surface copper is 2+, and a major species platinum is a metal. And further EDX analysis tells us the two species copper doesn't overlap with platinum, so it separates deposits on the surface of TiO2. On the best sample, which is only 0.1% of copper and 0.5 we consider planner, we get methane convert to carbon-2 as ethene and ethylene. And selectivity, which is here nearly 60%, with the other 40% is carbon dioxide. And activity, because it's a flow system, it can run as long as we want, so activity is very good, quite stable. And what quantum yield is about 0.5%. Now, based on the knowledge we have, we can see after excitation in TL2, electron transfer to PT, that's a metal, and that help reduction reaction, and hole transfer to copper oxide. So next one can help oxidize methane to CH3, two CH3 come together, get ethane, and this proton will react with oxygen gas plus electron to get water. So that's a process. And this table lists the results we found on methane converted to carbon-2. You see, majority use batch reactor. We are the first one use a flow reactor, and we achieved, I think, so far the best results in terms of yield of carbon-2. So that comes to the conclusion. The first one, we proved the feasibility of methane conversion at room temperature by photocatalysis, and we use atomic level N on TL2, achieved 97% selectivity to alcohol, and the conversion is 15%, which is 100 times better than previous results. And also proved the active species is FeOH. The drawback is we have to use peroxide. Very recently we use oxygen to convert methane in a flow reactor, and that's the first report. And the best catalyst we found is copper oxide and PT on TL2. This best catalyst gives us selectivity to carbon-2, 60%. And that is close to even the benchmark results achieved at high temperature by thermal catalysis. Finally, I should thank many students and postdocs in the group. I don't have to speak about. And also thank my collaborator at JFW Imperial College and Shaw at my university, Professor Richard Catlow in Cardiff University, and a few other collaborators in Sheffield, Japan, and China. And thank the funding support from UK Research Council and EU Epicenter Project and Liverpool Project, plus Newton Fund and other seed fund from different sources. Thank you for attention.